I lead the fundamental AI research at the Alan Turing Institute, where I'm also the interim chief scientist. I also hold a position as a professor at UCL. Firstly, just to pass on our thanks to EPSRC and the Alan Turing Institute for making this event today possible here. And just also to let you know that we'll be filming this event today, and so talks will be available online afterwards, so you'll be able to follow the discussion further there as well. So I'd like to start with a few brief opening words. I promise to keep this brief, but let me just start maybe a few hundred years ago. So since we're here at the Royal Society, I thought it would be pertinent to think back to the scientific revolution and see, how that could maybe help inform us and what we could learn from that about this AI revolution that we're living through today. And in fact, we may get some insights from that on how that AI revolution can feed back to potentially lead to another scientific revolution. So of course, when thinking about the scientific revolution, we have to start with Newton. So take a moment to consider the relationship between Newtonian mechanics and calculus for a moment, just to help set the scene. So the need to describe motion and forces essentially drove Newton to invent calculus. Then, once calculus existed, it matured as a mathematical framework, as a mathematical field in itself. But that didn't just serve mechanics, it actually fed back to revolutionize mechanics. Differential equations, dynamical systems, reformulations of Lagrangian and Hamiltonian mechanics then all followed. So the mathematical machinery that mechanics initially birthed then pointed the way to new science, towards quantum mechanics. So it's sometimes said that mechanics invented calculus, but then calculus reinvented mechanics. As another example, consider Fourier. So Fourier's series was developed to solve the heat equation, and this then birthed an entire new branch of mathematics, of analysis, of Fourier analysis or harmonic analysis. That then flowed back to solve countless more physical problems across waves, optics, communications, and many more beyond. Noether realized that conserved physical quantities, such as momentum, angular momentum, were all consequences of symmetry. Her insight then fueled the development of group and representation theory, which now underpins the standard model of particle physics. So in all of these problems, in all of these examples, a problem in the physical sciences has motivated new mathematics. That mathematics has then matured, developed in its own right, under its own logic, and that then flows back to transform the original science that motivated it. And in fact, often transforms areas far beyond that original area as well. So this feedback loop between mathematics and the physical sciences was in many ways a key engine of the scientific revolution. Progress accelerates when we close that feedback loop. This is true for AI itself. We hear a lot about an imminent intelligence explosion when we might close that loop with AI, with the next version of AI being developed by AI itself. But this is also true between AI and science as well. Although it does need a two-way street. So it's not just AI feeding into science, but also science feeding into AI. And I think, we're not quite there. We haven't quite fully closed this loop yet, but we're on the cusp of doing so, and the remarkable progress that will bring both in AI and in science. And of course, science is absolutely critical to our national posterity and national resilience. So I asked Gemini to make a quick graphic to depict this virtuous feedback loop between AI and science. And I think this is an example where we're not quite there with AI yet today. So I wouldn't necessarily read too much into this diagram, but the main point I wanted to get across is that it's through these connections between fields, by closing these feedback loops, that really is going to lead us to this next era of rapid progress. So I recently started blogging about some of these ideas. I know I'm extremely late to the game, but if you want to dig a little deeper into some of these connections between the scientific revolution and the AI revolution, you might be interested in a recent post there. But we're going to have an opportunity today to discuss these kind of interactions between AI and science in much more detail. We've got a fantastic lineup of keynote speakers for you here today, where we're going to learn a lot about how AI is impacting numerous scientific disciplines, from astronomy to material science, from climate science to clean energy generation with nuclear fusion. But beyond the science itself, we're also going to discuss how we can make AI for science work. What are the appropriate AI kind of principles or approaches that one should be thinking about or taking in science? So this is questions around physics or science itself, our kind of scientific models. What's the role that they can play alongside AI models? And should we be integrating these, what are often called inductive biases, into AI models, or rather purely letting the data speak for itself? Of course, for science, we want to, at the end of the day, understand underlying physical processes. So we want to be able to interpret these models. We're also going to discuss what the role of foundation models are in science. Also, there's been a huge rise in agentic workflows and AI scientists as well recently. So we're going to talk about that and try and understand where AI scientists can be useful and where the field is moving. We need to ensure AI approaches are trustworthy, which is really absolutely essential for scientific integrity. And finally, we're also going to touch on, how do we actually operationalize these models for science? So actually putting them into use in real-world scenarios and the benefits that they can realize. So this is our overview of the agenda. So just very briefly, we've got 2 keynote talks coming up, and then we'll have a series of lightning talks. So these will be very short talks by early career researchers, and there'll also be posters for each of those talks. So hopefully you'll get to see an overview of a lot of work that young researchers are doing, and then have the opportunity to discuss further over the coffee breaks around the posters. Then after lunch, we've got 2 more keynote speakers, another series of lightning talks before the coffee break, and then we'll wrap up with the final keynote talk and a panel discussion with all of the speakers, where we'll discuss many of those points I highlighted just recently.